the first test, official test, okay? And I love to call it test for divergence. Most of the textbooks are using test for the divergence. Some of the textbooks are naming this n-term divergence test, but you will probably see me writing test for divergence. This infinite series is divergent by test for divergence. And if you see me, if I will see this on the homework, the written homework assignment, I will be so happy because then I know that you're learning something from me. Okay, what this test is telling us, let's look at this. If the limit of the sequence A sub n does not exist or is different than 0, then the infinite summation, infinite series is divergent. No chance for convergence. Okay, that's mean, and especially this. I mean, of course, if the limit does not exist, if the limit is different than 0, then the infinite series is divergent. Do we understand? Do I have examples? I have some examples, but let me give you maybe this one: n+1 over n+5. If I will ask you this, is this infinite summation convergent or divergent? Convergent or divergent? n+1 over n+5. Of course, it's divergent. We may say, okay, this is 2 over 6 plus 3 over 7 plus 4 over 8. This is not telling me much, but at infinity, yes, how these terms behaves, where they go, what they approach. We can see 2 over 6, 3 over 7, 4 over 8, then 5 over 9, and so on. But what is the limit? How these terms behave at infinity? They are approaching 1. Yes, that's we can see they are getting closer to 1. Now, what we have to think, because that's sometimes is a common mistake, you will say that the sequence is convergent to 1, but the series is divergent. Because how we can connect that 1? We can say that, yes, these terms are almost 1. And we have to think, oh, wow, that 1 will be added, 1 plus 1 plus 1 plus 1, infinitely many times, because it's almost 1 at infinity. That means, of course, it's divergent. That means that's how we can think about the limit of the sequence. We're taking that number and adding. Okay? That means when the limit is different than 0, it's no chance for convergence. Then we can say right away, this infinite series is divergent. And now we have to have the reason by the test for divergence. Or we can say n-term divergence test. Okay, that's mean, please remember, that's where the 1 goes. We also know, what about this one? Let's say 1, let's say 2. What about 1 over n? 1, 1/2, 1/3, 1/4. How the terms behaves? How the terms behaves? At infinity, it's 0. Okay, it's 0. Then at some point, it will be almost 0. Almost 0. We will be adding almost 0. But what we know about this infinite series, it's actually, yes, it will be, because we still have to know what kind of 0 it is. And this 0 is kind of too big. But why I'm giving this example, even if the limit is 0, we know nothing. This one we know because it's harmonic. Yeah, harmonic is a good example. Harmonic series n is, of course, oh, no, something divergent. Okay, because even if the limit is 0, we know nothing. And also because how we can overuse this, if the limit is 0, we will say the infinite series is convergent. No, not good. First of all, when the limit is 0, we know nothing. We have to use different tests, different properties. And another thing, this is test for divergence. This is only testing divergence. That means only this condition. Yeah? How we can say it's convergent by the test for divergence doesn't fit, doesn't make sense. Okay, that means please remember, if the limit is different than 0, then we can stop, we done divergent by the test for divergence. Okay, good. But if the limit is 0, we know nothing. This test doesn't work, we're looking for the different tests. We will learn lots of them. Okay, show that this series is divergent. Is this series divergent? Why is divergent? Because what is the limit? The limit is, of course, 1/5, different than 0. We may think that, yeah, we will have like the first term, we will have a second term, because I don't want to calculate. And then eventually we will be adding 1/5, 1/5, 1/5. Of course, it's infinity. That's we can say divergent by the test for divergence and term divergence test. The limit is different than 0. No chance. Okay, good. Oh yeah, I have solution. What about arctangent of n? Yes, I can see arctangent of n. Let me do the, yes, we can say the first term is arctangent of 1 plus arctan of 2. And then eventually how these terms behaves at infinity. Actually, arctan of n at infinity. Yes. We have to think that we will be keep adding pi, almost pi over 2, pi over 2. Of course, this is infinity. Different than 0. Yes, this is divergent by test for divergence. And we can even draw this, and let's use the function. Oh, am I good? And pi over 2, oh, we don't need, because we will have tangent, arctangent of 1, arctangent of 2, 3, 4, 5, and then we can see almost pi over 2. Okay, okay, good, good. Again, my notes. If we find out that the limit of the sequence is different than 0, then no chance for convergence, divergent. If we find out that the limit is 0, then we know nothing. Okay, we know nothing about convergence or divergence, because if the limit is 0, the series can converge or diverge. We know that. Okay, good. What else I have? I have some property, linearity, but we know it's the same like when we have constant. Just see how to play with the sigma, because we're getting ready for more complex formulas. Constant times the formula that depends on n, we can put constant and just follow the formula. I mean, focus on the formula. Summation of the addition is addition of two summations. Summations of the difference is the difference of two summations. We know that from Calc 1. Also, I want you to know that like sometimes, because some of the tests will be like, they will be still good, but we will have certain condition. And if we can prove that formula satisfies all of this hypothesis, all of these conditions, then it's good. Then we can like use the test, yeah, the follow test that we will learn. And sometimes we will have the situation that the formula doesn't satisfy the condition like from the beginning. Like let's say for the first, like let's say we want the entire formula to be decreasing, but the formula, the sequence could be like increasing and then decreasing. That means at some point, let's say at n equals to 40. Oh, okay, 440. Yeah, and this is good because if we avoid couple of finite terms, this is not affecting, yes, like the infinity. That means it's fine. We can still say this is like this works starting from n equals to 40, and skipping the finite number is not affecting convergence. Okay, that means just I want to tell you that if we good, yes, at some point it's like eventually, yeah, it's good. Okay, just a note. Okay, exercise. Let's see if you can earn your points on the test. True or false? Let's think. Statement A. There exists an example of a divergent series A sub n whose terms satisfy this limit at infinity of A sub n equals to 0. Can you give me an example or not? If you can give me an example, the statement is true. There exists an example. Limit 0, but divergent. Yes, of course. 1 over n. Equals to 1. I was going to say 1 to infinity. It is divergent, harmonic, and the limit is 0. Yes, that's true. And I can say harmonic. Okay, true, correct. What about B? There exists an example of a convergent series A sub n whose terms satisfies that the limit is 0. All like everything what is convergent, yes, everything what is convergent, it will be the limit must be, yes, limit must be 0. Yes, and we can say 1 over n squared if we remember this, or one of the geometric one. Let's say 1/2 to the power of n. Yeah? All of the limits goes to 0. That means yes, this is true. Okay. What about this one? Divergent, whose limit of the terms of the sequence is 1. Yeah. Yes, it will be also true. Can you give me an example? Yeah, just probably the ratio of two polynomials. We just did something, yes, n plus 1, n plus 5 maybe. The limit is 1, and it is divergent by the test for divergence. Limit of that, it is 1. And it is divergent, of course. Okay, and what about D? Convergent. Then the limit is 1. No, that's false. If the limit is 1, limit different than 0, it will be always divergent. That's false. No such an example. No such a number. No such a name. Do you know that song? No such an. Oh, I will not sing. Oh my gosh, no. No, you don't. You know the song. No such a number, no such a name. He was sending a letter, and the letter was coming back. And it says no such a number, no such a song, no such a name. And then he was sending and sending, hoping that she will reply. But then he said, at the end of the song, I will go and I will actually hand it that letter. If I will still get the message, no such a name, I will know what this means. I will not bother her. Oh, okay. I'm not telling you. You will find out and you will tell me next week. Probably if I will sing a little bit, you will know, but I will not. Yeah. Yes. Return to sender. Do you know that song? I love Elvis, but I'm old. Please look, it's such it's nice song because it's nice tune, but it's sad, yes. Oh, I always feel like it. Okay, yes. Oh, okay. Okay. Yes, I mean, I don't know. I think that's the interpretation because he was sending and was returned to sender. Yeah, return to sender. Nice song. Okay, that's me no such an example. Okay, you were in Graceland before. Okay, let's keep working because we have a couple of nice examples. I have to test you, but we have nice break. Yeah, we could put the song. Okay, what's the answer to exercise number 16? Oh, Tonglar, you, of course, you the excellent student. Everybody's excellent, but oh, I don't even have to. Okay, that's what we have. We have A sub n be the infinite series with the sequence of the partial sum. And yes, we have a formula. Now we have to be, yes, we have to be really careful. Okay, that means now this is the partial sum. That means the partial sum, yes, like if we would like to find the sum, do you remember like I was with the notation, I think I confused myself. We can say, yes, the sum exists and it will be nice to compute the limit. And yes, all of my students know what is this limit. Beautiful, e to the power of 5, convergent. But let me ask you, please be really careful. Let's say A, let's say B. Is this series convergent? No, convergent or divergent, let's say this way. And the formula is like this. Please be really careful. I changed the question almost completely. Is this infinite series convergent or divergent? Yes. It is divergent, yes. Is divergent by test for divergence. Thank you. Because the limit, yes, because that's not the partial sum anymore. It's a formula. Yeah, yes. The limit is different than 0. That means at some point, if we will list the terms and keep adding, because sigma is addition, we will be adding e to the 5, e to the 5, e to the 5. Yes, okay. That means this one is, let me say, the convergent. Okay, because it's different, because that's partial sum. Now I took that formula as a formula of the sequence, actually, that we're adding, not the partial sum. Okay. Yeah, don't make, you will not make the mistake. I know. Okay, another one. Okay, nice question. Each question is important, you know that. It will simplify our life. Given that the series A sub n and S sub n is a partial sum. Yes, we can see S sub n is the partial sum of the infinite series. And with the B, it's nth partial sum. And we have the formula for the partial sum. Beautiful. 8 over 5 over n squared. Now, find A sub 3, find the sum of the series and show that the series is diverges, and find the limit of A sub n. Okay, we don't have the formula for A sub n, but hopefully we will be able to find. Okay, how we can find A sub 3? Only having partial sum. Yes, because what about S sub 3? 1, 2, 3, correct? And we can compute because we can compute, and actually, no, let me write this. S sub 2, maybe this way, maybe I don't. That means when we will take s sub 3 minus s sub 2, we will just end up with the third term, correct? Yes, yeah. Okay, and s sub 3 will be 8 minus 5 over 3 squared, because we have the formula, minus 8, 5 over 2 squared, yes? Just using this formula. 8 minus 8, 5 over 4 minus 5 over 9. Oh, I don't know. Yes? Okay, 45 minus 20, 36. What do you have? Yes, correct. Yeah, just even if we will on the test, even if we leave that answer, but yes, that's not bad. Yes, everybody is correct. Even me, good. Okay, perfect. That's the value for a sub 3. Now, what about B? What we have to do to find the sum? Yes, we just have to, we know that if that sum exists, let's assume that exists, we have to find a limit of the partial sum. And you are right, limit at infinity of the formula okay, I will change for the small. It is 8. That means, yes, this is convergent. The infinite summation, yeah, converges to 8. Beautiful. Then what's the answer for the C? If the series is convergent, the limit always is 0. It has to be 0 because we will be keep adding that 0, and that 0 is, if it's, yeah, then we know that it's small enough. Small enough. Good. Really nice question. Let's say 0. Okay. The next one. Actually, I can leave it for you because it's identical. Yes, it's identical. Let me check. 19. This one is also identical that we did the previous one. Okay, let's just do 1, 2, 3, 4, 5, 6. Let's just focus on those because this one I don't want to, you will see, it's identical to the true and false. I want you to do it. It's just different wording. Okay. Now, that's what I was kind of saying, that when you will see the list of the infinite series, you will like know almost right away, convergent, divergent, convergent, divergent. And now we still don't have enough tools, enough tests. Next week will be even more colorful, but it's fine. We can still answer. Okay. The question is determine whether the series is convergent or divergent and always justify. That's mean, what about A? 5 over n. Yeah, we can keep 5. It doesn't matter. It's just the constant. We can say, yes, we can say it's divergent. And what is the justification at the moment? Divergent, harmonic, of course. That's what we can use as a proof. Harmonic series. It's good. Okay, what about this one? B, convergent or divergent? Divergent. Why? Divergent, beautiful, by test for divergence. Thank you, because what is the limit at infinity of the sequence? 4n squared, and I don't even need to do this. 1/4, thank you, different than 0. If the limit is different than 0, test for divergence. Good. Really good. Okay, that's mean not 1/4 doesn't indicate convergence. Sequence is convergent, but not the summation of that terms. Okay, C, arctangent of n. Arctangent of n, convergent or divergent? It's a nice example because the limit at infinity is pi over 4, divergent, different than 0. Divergent, by test for divergence. Beautiful. Okay, what about D? D we have to probably work on the limit. Yes, it is divergent, but what I will do, I will say X, arctangent. You probably know why I put X. Yes, the limit will be 1, but it's infinity. 1 over big is small, arctangent of small is 0. It's actually indeterminate form. That we have to use the L'Hopital rule. And I think, yes, the limit will be 1. I think the limit will be 1. That means limit is different than 0. You can try. You can keep maybe arctangent on the top, 1 over x in the denominator, and yeah, use the L'Hopital rule. Divergent. Yeah, this one I will definitely spend time on computing the limit, right? To the limit, but the limit will be 1. Okay, A, B, C, D, E. What about E? Of course, divergent by test for divergence. What is the limit? Oh, that's not really challenge for my students. 1/4, yes. What about F? Please tell me the limit. Natural log. Because when we have subtraction, we can divide. Yes, it's natural log of 1/2. Different than 0. That means we will be adding the first term, the second term, and then eventually we will be keep adding that terms. Writing infinity is not a proper, but we know it's divergent by test for divergence. Okay, A, B, C, D, E, F, G. Is G also divergent? Divergent. We know the limit. What is the limit? Really quickly, I want to double check. Yes, different than 0. Okay, what about this limit? Everybody agree? Because this one is 1, I mean 1 over n, 1 over big number small, 0. 1, different than 0. Yes, divergent by test for divergence. By test for divergence.